Hello, everyone, and welcome to section 4.5, where we're going to talk about derivatives and the shape of the graph. Over there is Theodore. He is not actually sleeping, but he is a little shy. Merry Christmas, everyone. It is currently not Christmas. Without further ado, basically, this section is kind of like the last section in that it is connecting information about graphs of functions with the derivative. So kind of trying to go full circle here and really go back to what a derivative is and how does it connect with graphs. And specifically, we're going to start by talking about the first derivative test. Now, this relates to something in 4.3. If you remember in 4.3, we talked about how to find critical points. We could do that by hand. We talked about finding global or absolute extrema, which is basically just find all the candidates, endpoints, critical points, and pick the biggest or the smallest, but we never actually found local extrema in 4.3. That's because we needed something like the first derivative test or the second derivative test, which we are going to also get to later on in this section. So we're going to start by just doing some definitions and connecting it to the previous section, actually tying things together, which is always fun for me to do. So let's start with the definition. A function f is increasing if it's going up. That's not the definition we're doing, but that's basically what it is. F is increasing at x if the derivative of f at x is positive. So derivative is the slope. Derivative is the rate of change. So if it has a positive slope, that means it's going up. Okay, positive slope means going up, means increasing. All of these are always from left to right. Okay, and similarly, f is decreasing. I bet you know where this is going, even if you have never seen this before. Well, if it's increasing for a positive derivative, well, it's decreasing, blah, 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 if the derivative is negative. Exactly. All right. So again, this can pop up in a couple of different ways. You know, maybe we have something like this. This is an increasing function. This is also an increasing function. Now, these are two types of increasing functions. We'll talk later in this video about the differences between them. But in both, let's look at some tangent lines. In both of these situations, right? Here's the tangent line right here. The slope of the tangent line is positive, right? Tangent line is a positive slope. The tangent line is going up. And again, here's an even steeper tangent line. So this, not only is the slope positive here, not only is the function increasing, but the slopes are also getting bigger. And in the second one, again, this is also an increasing function. If you draw some tangent lines, notice that both of these tangent lines have positive slopes. On the first one, the slopes were increasing, and the second one, the slopes are decreasing. But in both of them, the function itself is increasing. The function is increasing, the derivative is positive. All right, and you could do, again, these ones are increasing. You could do the same thing for decreasing functions. Functions that are going down, they will have a negative derivative. You can have something going down like this, or again, something going down like this. They're both going down. Any tangent line that we draw will have a negative slope. The slope of the tangent line, remember, is just the slope. It's just the derivative. So negative derivative, negative slope, decreasing. Positive derivative, positive slope, increasing. And again, it can happen in kind of two different ways that we'll talk about when we talk about concavity. Okie dokie. So let's kind of connect this to critical points in the past. We haven't mentioned the first derivative test yet, but I want you to be thinking about the first derivatives. What does the first derivative tell us? The first derivative tells us whether the function is increasing or decreasing. If the first derivative is positive, the function's increasing. If the first derivative is negative, the function is decreasing. So let's kind of look at some of the shapes that we looked at in the past when we were looking at critical points. So feel free to copy all of these curves, and also keep in mind, where are the critical points here? Where are the local extrema? I'm going to draw a bunch of these down, and then we're going to talk about them all. The actual values don't matter, so I'm just drawing the shapes, like so. Let's have a conversation. So first off, critical points. We talked about that earlier. Let's draw the critical points in red. Critical points are when the derivative is equal to 0 or when the derivative doesn't exist. Horizontal tangent line, derivative doesn't exist. Horizontal tangent line, derivative doesn't exist at the asymptote, but the function doesn't exist either, so there is no critical point. This is supposed to be getting horizontal, not actually being horizontal. Derivative doesn't exist. Derivative equals 0. Derivative is undefined. Let's look at two more as well. If we look at some piecewise functions, then remember that these also have critical points. And these piecewise functions, again, here's a critical point, here's a critical point, here is a critical point. So what's the relationship between these critical points, local extrema, and increasing and decreasing? Well, this is going to be a local min. This is going to be a local max. And what can we say about the derivative here? Bless me. What can we say about the derivative at these 2 points? Well, the function, let's look at this red point. Well, they're all red. This function is decreasing to the left. The derivative is negative. The function is increasing to the right. If it's decreasing and then increasing, we have a local minimum. Interesting. Function is increasing to the left at this point, right? As we go left to right, we're going up, and then we're going down. Positive derivative, negative derivative. To the left, we're going up. To the right, we're going down. We have a local max. Interesting. Next one. This is again a local max. As we approach from the left, we're going up. And then as we leave it to the right, we're going down. The derivative goes from positive to negative, increasing to decreasing. We have a local max. Okay, here, let's keep these. I've been erasing them, but let's keep these. Let's see if we can notice a pattern. Here we have a local max. Well, what's happening? Well, from the left, the function is increasing. The derivative is positive. To the right, the function's decreasing. The derivative is negative. It's going down. And you can see actually that this is the case for all of these on this page. Decreasing, increasing, local min. This one itself, this is not a local min or a local max, right? The function from the left is going up, positive derivative, and to the right, it's also going up. In this case, it's going up in both directions. There's no local extrema. And here, again, it's going up from the left, and it's still going up to the right. If you look at the derivatives on this one, again, there's no local extrema. So what we have on this page is basically the first derivative test. If there's a critical point, and the function goes from decreasing to increasing, like in blue, that's a local minimum. We can find that with looking at the first derivative. Decreasing means negative derivative, negative slope. Increasing means positive derivative, positive slope. But if the sign of the derivative doesn't change, right? Here, negative to positive, positive to negative, positive to negative. But if the sign of that derivative doesn't change, positive, positive, or negative, negative, and there's no local extremum. That's basically the first derivative test. And then this last thing is just, again, a little thing to watch out for. Here, again, we have a local min. But at this other point, right, to the left, we're increasing, and to the right, we're decreasing. You would think that there's a local max here. But there's no local max or local min here. This is not a local extremum. So this is the weird ones. So what's the difference, right? What's the difference between this case where it goes up and then down, and then all of these cases, these green cases where it goes up and then down? What's the big difference between these maxes? Up and then down is a local max. And this point where up and then down is not a local max. Well, it's not continuous. It's going to turn out that continuity is important. And again, over here, this one is actually going up and then up, but it is a local max. And again, what's the difference? Continuity. So continuity is going to be a really nice thing for us to apply the first derivative test. These two things on this page, don't worry too much about. These are just why we have assumptions. Like a lot of times when I have theorems, when I give you guys theorems or I give you guys properties, we have these assumptions. I think it's interesting sometimes to consider, why do we need those assumptions? And these are some of the examples for why those assumptions are needed. Okay, so let's kind of put that all together to finish this video. Theorem is going to be the first derivative test. I don't have a good abbreviation for this. I love abbreviations, but somehow I don't have one here. And it says, suppose f is continuous. That's the very, very start on an interval I. And again, the interval I needs to contain a critical point, C. So again, this is continuous. This is critical point. And this is why we need this. Because if we don't have that we're continuous on some interval around the critical point, right? It doesn't have to be continuous everywhere, right? We could use a first derivative test here, even though the function's not continuous. It just has to be continuous close by, continuous somewhere that contains that point. Doesn't have to be everywhere, but continuity is going to matter. Suppose f is continuous on some interval I containing a critical point C. So if f is differentiable, again, these are all abbreviations and definitions that we've talked about earlier. If f is differentiable on the interval, meaning it's differentiable on every point in that interval, except it doesn't technically have to be at C itself. And again, that's going to be these sorts of situations. We actually don't need it to be differentiable at the point. And again, that's kind of makes sense because for critical points are when the derivative equals 0 or when the derivative is undefined. So a lot of times these local extrema will have undefined derivatives. And that's okay, actually. All that matters is that the derivative exists on both sides of the critical point, but it actually doesn't need to exist at the critical point itself. So that's what this is referring to. All right. And that's a very, very good little exception right here. All right, then let's actually get to the test. So it's a test. What are we testing? We're testing the derivative. If f prime, the derivative, if f prime goes from positive to negative, if at C, then f of C is a local what? And the way to remember is to think about increasing and decreasing. F prime is positive. That means it's increasing. And then negative. That means it's decreasing. Well, are we at the top here or are we at the bottom? We're at the top. It has to be a local max. And that's how you can remember, okay? And similarly, if f prime goes from negative to positive at C, then f of C is a what? A local min. All right. So this first one you can think of as going positive derivative to negative derivative. Increasing to decreasing, it's going to be a local max. Negative derivative to positive derivative, decreasing to increasing, that's a local min. And the last case is that yellow case. If f prime does not change signs, then there's no local extrema. I'm going to write behind my head again, aren't I? That word behind my head says extremum. And we have like this case in this last one. All right. That's the first derivative test. We'll use it in the next video, get lots of practice, and then move on, talk about the second derivative. What does the second derivative have to do with a graph? And we can actually use the second derivative as well to find and classify local extrema. Extrema. I get those two words confused all the time. And then we throw it all together, and there's a lot of fun stuff in this. If you like graphs, and if you don't like graphs, there's a lot of fun stuff in this section. It should be fine. Let me know if you have questions. We're in it together. Have a good day.